Hey, it's Mr. Juniper. We are learning about states of matter and we want to specifically investigate phase changes. Chapter 3, Section 3. Let's get to it. Chapter 3, Section 3 on phase changes, presented by me, Mr. Juniper. Looking at a large iceberg, there is enough fresh water to supply many people, millions of people, with water for the year. Of course, as it moves into warmer areas, the ice changes to liquid water and melts. The question is, what is happening at the molecular level with those water molecules? What happens when a substance changes from one phase to another? First off, there are 6 common phase changes that we're going to want to be familiar with. What are they? Well, the 6 phase changes are reversible physical changes that occur when a substance changes from one state to another. So we're talking about melting, freezing, vaporization, condensation, sublimation, and deposition. Let's look at a diagram. This lists the 6 physical changes that can occur among solid, liquids, and gases. And the arrows represent changes. So that's what we call a phase change, when one state of matter turns into another. And all the phase changes have certain characteristics that are important. So first we're going to start off with, let's just start off with a solid, where the particles are packed and locked in place, and the intermolecular forces are strong enough to freeze whatever that substance is. Quite easily, and you are definitely familiar with the fact that if that solid absorbs energy, it'll melt. If we take a liquid and we remove energy from it, cool it off if you want to think of it that way, it freezes. So those are super easy. The next ones get a tiny bit more detailed. Again, I'll look into this and zoom in. When we are going from a liquid to a gas, liquids can boil or evaporate. Both of those are forms of vaporization. The molecules gain enough energy that they're no longer swimming next to each other, packed in pretty close. They become a gas. They become a vapor. And if a gas loses energy, it goes through the process of condensation, where all the gas molecules form, well, in the case of water, little water droplets, clouds, fog, your breath on a cold day, all forms of condensation. The least common phase changes, as I go in here, would be the direct phase changes between a solid and a gas. As we will talk about and see with dry ice, solids can turn directly into a gas through sublimation. This actually happens to water ice as well, to a much smaller, slower degree. And the very interesting phase change that we want to also add in is that gases can go through deposition and become solids. This becomes critically important when we want to understand snowflakes. Snow and some forms of frost are not just frozen water. They are actually water vapor in a supersaturated air mixture being deposited and forming wonderful crystal structures. What about the most common state of matter, plasmas? Where do they fit in with this? Well, if you take a gas and you ionize it, you disassociate the electrons from the protons and nucleus, and it becomes, well, a plasma. This is where we start to get more detailed, and we call this high school chemistry. When we talk about what happens to the substance's temperature and a system's energy during a phase change. When ice melts, the temperature of that substance actually doesn't change. And in fact, when ice freezes, it actually doesn't get any colder. You still have to remove energy to freeze water, but that actually all goes into slowing the particles and going into the phase change rather than lowering the temperature. The graph given in the textbook is for a substance, it's naphthalene, which is used in mothballs. And what this graph shows is a solid piece, and it gets heated. Notice, this is kind of critical, and we'll see this with water as well. As you add energy, the temperature is going to go up. But what happens as this naphthalene melts is it actually plateaus. And this is the melting point of this substance, about 80 degrees Celsius. And what is happening as you heat that is that all the energy from the stove or the fire, whatever you're using to heat it, the hot plate, all that energy is going in to break apart those intermolecular forces that have frozen the naphthalene together, and now it is melting. All that energy goes into melting it, not into creating a warmer mix. So the temperature remains at 80 C. We can see that after about 8 minutes, all of the naphthalene is melted, and so then the liquid starts to gain temperature. All the energy then goes into actually heating the substance. As this text states, if liquid naphthalene is cooled, its temperature will drop until it reaches 80 C, and it'll remain at that temperature until it freezes. The temperature at which a substance freezes, its freezing point, it's the same, it's identical to the temperature at which it melts. If liquid naphthalene is heated, its temperature could keep rising until it goes to 218 degrees C, and then it's going to flatten out again, because that's the boiling point. So until the boiling is all complete, naphthalene can't get above 218 degrees Celsius. It's similar to water. If you are freezing water, it goes down to 32 until it's all frozen. I'm talking Fahrenheit here, using our American customary units of temperature. Likewise, when you boil water, you can't get it over 212 degrees. All the energy you pour into that goes into the phase change. So when we're talking about phase changes, energy is transferred between a substance and its surroundings, and the direction of the transfer depends on what kind of phase change is happening. Either energy is absorbed or energy is released during a phase change. Let's look at some examples. Here's an ice sculpture in Japan, very cool, and it's in a nice sunny spot. Looks like the sun's out, so perhaps it's over 0 Celsius, 32 Fahrenheit. And if that is the case, the ice is going to absorb the energy, and then that's going to start the process of melting. During an endothermic change, the system absorbs energy from its surroundings. That is like ice melting. That is like water boiling. They need more energy, and they have to get that energy from the surroundings. In fact, we can measure how much energy this is. A gram of ice absorbs 334 joules of energy. Now, joules are very small units, like calories. So when we eat food and we consume calories of energy, food calories are a big unit of energy. These joules that we'll use in our class are very small units of energy. The amount of energy is called the heat of fusion. This is one of the most difficult concepts we talk about. The heat of fusion varies from substance to substance. So ice doesn't get warmer as it melts. In fact, it will make its surroundings colder. That's why you put ice in drinks. As the ice melts, not only is it possibly below freezing point, but even if it's just at the freezing point, as it goes through the phase change and melts, it is an endothermic change and it absorbs the heat from the liquid that you're drinking, and it can make drinks cold. In a bizarre twist, energy is released as ice forms. So here's an example, and you will see this in certain farms. They will spray water on crops before it's going to get too cold to protect the crops. Here's what happens. Energy is released as ice forms, and it keeps the plants from freezing at temperatures slightly below zero. So even though the ice is frozen, the plants stay warm. This is somewhat counterintuitive. As water freezes, liquid water freezes, it actually has to lose energy, which actually can help protect the plant. So a gram of water, it releases energy, 334 joules of energy, to its surroundings. It's the same amount of energy that's absorbed when a gram of ice melts. It's just in the opposite process. When ice melts, the energy goes in to the ice, endothermic. When water freezes, the energy leaves the water, and that is called exothermic. As water freezes, it releases heat. As steam condenses, the same process occurs. It releases heat. That's actually why boiling water can be very dangerous. If you get steam condensing on your skin, it can give you a terrible burn, not just because it's very hot, but it's an exothermic phase change. Exothermic changes are where a system releases energy to its surroundings. We will talk about that with chemical reactions as well, but we can talk about it with these physical changes between different phases. Let's look at the arrangement of the water molecules during melting and freezing. Don't forget, a solid has tightly packed particles, and they are locked in place. In a liquid, the particles are still close together, but they are no longer locked. They are free to move. Keep in mind that the arrangement of molecules in water becomes less orderly when it melts, and more orderly as it freezes. If we look at water, it's actually denser in its liquid form because the particles can swim closer together. When it forms ice, a crystal pattern is formed because of the polar nature of water molecules. Oxygen is slightly negative, hydrogen becomes slightly positive, and we can see it makes a nice hexagonal organization that actually is less dense than the liquid form. This is why ice floats. In ice, the attractions between the water molecules keep the molecules in a fixed position. As it gains energy, the kinetic energy of those molecules increases, and it allows it to melt, and then the temperature can start to rise. When an ice cube is removed from a freezer, the heat flows from the air into the ice. That is what we call an endothermic change. As the ice gains energy, the molecules vibrate more quickly. Of course, the melting point of water is 0 degrees Celsius, and some molecules gain enough energy to overcome the attractions and move from their fixed position. When all the molecules have enough energy to move, we say that the melting is complete. Water and a lot of the substances we will look at form crystalline solids. They have a distinct melting point. The textbook doesn't mention that there are amorphous solids as well. These are solids like butter and plastic that get soft as they get heated, and they don't have a distinct melting point. Often, people think of cold temperatures when they hear the term freezing. But substances that are solids at room temperature sometimes freeze at temperatures that are quite high. For example, silicon freezes at 1,412 degrees Celsius. Metals have very high freezing points. That's why we always see them as solids, except mercury, I suppose. Any energy removed after the freezing is complete decreases the average kinetic energy of the molecules, and the temperature drops. If you take liquid water and place it in a freezer think of the energy. The liquid water's energy flows out into the air of the colder freezer. There is no such thing as cold. There is only things that are less hot. So, as this happens, the water cools. As the average kinetic energy of its molecules decreases, they start moving more slowly. And finally, at the freezing point of water, some of the molecules move slow enough for the attractions between molecules, those intermolecular forces, to lock them in place. When all the molecules have been drawn into an orderly arrangement, freezing is complete. The phase change in which a substance changes from a liquid into a gas, vaporization. So if you want to vaporize something, it is an endothermic process, which means it absorbs energy. So if you want to vaporize water, it needs to absorb energy. In fact, 1 gram of water has to gain 2,261 joules of energy when it vaporizes. This amount of energy is called the heat of vaporization. So we have the heat of fusion, which has to do with the latent energy, the latent heat from changing phases from a solid to a liquid or a liquid to a solid. And then we have this heat of vaporization, which is the heat that it takes to turn a liquid into a gas. Or likewise, how much energy is released when a gas turns back into a liquid through condensation. And this is a physical property. The heat of vaporization varies from substance to substance. So in a refrigerator, phase changes keep food cold. We can think about this very advanced concept. Energy from inside the food compartment is used to change a liquid to a gas in the evaporator. So you put something in the refrigerator and you want to cool it down. So it has relatively more heat. That heat goes into the liquid in the refrigerator and it vaporizes it. Energy is released then when the gas gets turned back into a liquid by a compressor. So if you listen to a refrigerator, it has a compressor, which is a motor that's working to turn that gas back into a liquid. That extra heat, as the gas turns back into a liquid, then gets ejected out of the back of the refrigerator. And so you should feel warm air coming out of your refrigerator. That is the heat being let off. During these phase changes, energy flows from the inside of the refrigerator to the outside, takes that electrical energy and ends up turning it into heat. And that is able to suck the heat out of the food and make it colder. There is no such thing as cold. There's just less hot. And so a refrigerator makes that liquid change phase and suck heat out of the food and then ejects it into the room. Here's just another visualization of it. So we have energy from the food compartment going into the evaporator. Then that gas goes back down to the compressor. And what the compressor does is turns it back into a liquid so that it can then evaporate again, vaporize. And that takes a lot of heat to run the compressor. Let's think about evaporation. After a rain shower on a sunny, warm day, you notice puddles of water, and after a few hours, puddles are gone. Evaporation is a change in a substance from a liquid to a gas, but the temperatures are below the substance boiling point. Evaporation takes place only at the surface of a liquid and occurs at temperatures below the boiling point. Here's a bird feeder, and the water level in the bird bath will decrease over time. Some of the molecules near the surface are moving fast enough to escape as a liquid, and they become water vapor. The greater the surface area, the faster the water will evaporate. Also, temperature will have a direct influence on how fast the liquid evaporates. When water evaporates in a closed container, water vapor collects above the liquid, and the pressure caused by the collisions of this vapor in the walls of the container, it's called vapor pressure. The vapor pressure of water increases as the temperature increases. At higher temperatures, more water molecules have enough kinetic energy to overcome the attractions of other molecules in the liquid. So let's look at boiling. How are evaporation and boiling different? Well, vaporization could happen at room temperature, which would be evaporation, or at higher temperatures, which generally we would consider boiling, especially with water. As you heat a pot of water, the temperature and the vapor pressure of the water increase. So vapor pressure is a property of a liquid of how much it is trying to escape. It is a physical property of liquids, and each liquid has different vapor pressures. At 100 degrees Celsius, some molecules below the surface of the liquid even have enough kinetic energy to overcome the attraction of neighboring molecules. The boiling point of liquids depends on where you are. If you go up in altitude, there's less atmospheric pressure, and so liquids boil at lower temperatures. That's why if you ever travel to Denver or to very high cities, you have to boil pasta longer because the temperature at which the water boils is closer to 200 degrees Fahrenheit as opposed to 212 degrees. This also applies thinking about cooking with a pressure cooker. What that does is increases the temperature at which water boils so that you can cook foods faster. Basic facts: the temperature at which water boils is the boiling point, and keep in mind boiling takes place throughout the liquid. The boiling point of a substance depends on the atmospheric pressure, as I mentioned. Normal boiling point of water will always say at sea level, 100 degrees Celsius. The reverse of vaporization is condensation, and condensation is a phase change in which a substance changes from a gas to a liquid. Condensation is exothermic. It releases energy. Condensation is responsible for morning dew and the fog that forms on a mirror when you take a shower. Let's talk about probably the most curious phase changes. Dry ice. Dry ice is a common name for solid carbon dioxide. Carbon dioxide does not form a liquid as its temperature rises. At room temperature, dry ice goes directly from a solid to a colorless gas. It's called sublimation. That is the phase change in which a substance goes from a solid to a gas. And what happens is sublimation is an endothermic change. It absorbs energy. As dry ice sublimes, that cold carbon dioxide causes water vapor in the air to condense and form clouds. You cannot see carbon dioxide gas. So the smoke-looking stuff is actually water vapor that is then cooling off, losing enough energy to condense. Here's a technician hanging up a mosquito trap, and some traps use lures baited with dry ice because mosquitoes like carbon dioxide, and it's a pretty easy way to produce carbon dioxide at regular temperatures. Now, when a gas goes directly into a solid without having a liquid form, it's called deposition. This is exothermic. It releases heat, which is kind of counterintuitive in a way. When a gas is turning into a solid, it is the reverse of sublimation. And this happens with frost on windows. It happens when water vapor hits glass. And it also happens, most importantly, I think, in snowflakes. Snowflakes form through the process of deposition, where water vapor in a supersaturated atmosphere turns directly into a solid crystal. Beautiful. There's all sorts of different shapes. There's facets and all types of neat patterns, all based on hexagons, 6 sides, and that is because of the inherent nature of the water molecule, that it likes to form 6-sided shapes. That's it for phase changes. A lot of stuff is going on here. We're talking about the basic phase changes, but we're also talking about how energy is being transferred through these, talking about some of these phase changes as absorbing energy and being endothermic. Some of the phase changes give off heat energy and are exothermic. And we also talk about how it takes energy to go through a phase change. That's why the temperature doesn't change. It takes energy either released or absorbed when the molecules have to rearrange themselves and become a new state of matter. That's what we've got. Thanks for your attention, and I hope this helped.